So in this video, we can finish up our work on transforming nonlinear data so that we can use linear regression techniques. In this video, we're going to use logarithms. We're going to use transformations involving logarithms to find a power model or an exponential model that describes the relationship between two variables that we're going to make predictions using the model. And the second piece, we're going to look at which of many transformations does a better job of producing a linear relationship. I'll introduce the concept that that's a thing we might need to do, and then we'll post another video we're showing you kind of the back end work, what it would look like if you're using a graphing calculator to do that efficiently. So in the last video, we were looking at a power function, a specific power function involving length of fish and weight of fish. And we were given a clue that the cubic relationship was really what you would expect to find between length and weight. And then in the problems we did, they gave you some hints on that also. And the whole time I was thinking to myself, but what if you don't have the knowledge you need to pick a transformation to decide to cube this or cube root that? Well, what comes along to save us is a little unexpected. So this is your same example from before with the length of the fish and the width of the fish. And what we're going to use is we're going to use the fact that for any power model, whether it's cubic, quadratic, quartic, whatever, taking the log of both variables is going to actually create linearity. The reason for that algebraically is in the textbook, but right now that's not the purpose of this video. It's to give you some confidence that if you had your x values and your y values, and instead of plotting x versus y, which we can see is not linear, instead you took the log of the x and the log of the y and paired those up, you would end up with a linear relationship. And that's not just for this cubic fish problem, that's for any power model. At that point then, you could do your regression analysis and you would have all the tools available to you. Specifically, we could write the linear model that relates our input, not our input length though, our input log of length in a linear fashion to log of weight. And we could then use this thing to make predictions. You'll notice that I'm jumping past actually writing the power model. This is apparently a power model that we could write the equation for this thing, but right now we're just going right past that. We're using this linear representation to do a prediction. And that's because the algebra involving logarithms gets a little challenging, and I wanted to start with the most accessible. So plugging in 36 where it belongs and evaluating the right-hand side with the help of a calculator, we now have this. And at this point, it's a reminder that we had rules of logarithms and techniques in logarithms, including one where we said, if you know it's a logarithmic equation and you want to try to solve for the variable here, you might want to rewrite it as an exponential. And a help to do that is to remind yourself that log with, this is the common log with no base is base 10. So you can remind yourself my base is 10 when I write it as an exponential, and a log is an exponent. So this is the exponent that goes on 10. And then the overall relationship is this: 10 to the 2.846 is equal to the predicted weight, which is very similar to the predicted weight that we saw last time when we did different methods to get the same prediction. So what about this other piece of the objective, to find a power model? Well, this is the linear model. And if you wanted to represent that as the power model, you're going to have to do some algebra with this expression to get your power model, which is your predicted weight y is equal to a times your variable length to some power. And we would expect that power to be close to 3 because of yesterday's work. So what's the algebra that we're going to use for that? Well, the first thing we're going to do is we're again going to change form from a log expression to an exponential one, where 10 is your base, this side of the equation is your exponent, and weight, predicted weight, is your other side of the equation, is your power. So next we need to use an exponent rule, and we're used to using this exponent rule this way. When you multiply, you keep the base and add the exponents. But we could also use the rule from right to left. If you have an exponential expression where your exponent is a sum, you could split that out as 2 factors, and that's what we're going to do over here. So the negative 1.899 is an exponent on the 10, and so is the 3.04. Now, why are we doing that? We're trying more and more to get this variable by itself, and the more you can get away from it, the closer you get. The next step is going to call for this rule. There's a logarithm rule that you might remember where if you have the log base b of a to the c, then the c doesn't need to stay as an exponent. It can become a coefficient. So that's what we have going on here. But again, it's not from left to right, it's from right to left. We have a coefficient in front of a log. We have a coefficient in front of a log. So we can take that 3.04, we can swing it up to be an exponent on, in this case, length. And we're starting to now get a little bit closer to what we want, where your length, your variable to a power is a part of your power rule. But what is not part of our power rule is this. Well, here's another log rule. B to the log base B of A, when this base matches that base, there's a lot of unnecessary writing here. B to the log base B of A evaluates to just A. And there's good reasons for that we learned in pre-calc. For now, we're just going to use it. Since this base 10 and this base 10 match each other, this whole factor right here turns into just length to 3.014. So there's our power rule. So from a linear rule, you could make a prediction without doing all this work. But if you're asked to come up with a power rule, you're going to have to utilize all that algebra. So it's here as a reference. And then finally, determining which of many transformations does a better job of producing a linear relationship. Let's see what we're talking about. So for this one, the context is going to be transistors on a microchip. Apparently it doubles about every 18 months. And when you hear that, you might have an idea that that's an exponential relationship. But let's pretend you didn't know that. Let's pretend you were thinking, once you graph this thing, the number of years since 1970 versus transistors, you see a really steep growth, and you think that's, let me think that maybe that's part of a quadratic, or maybe that's part of a cubic or a quartic. Maybe it's an exponent, maybe it's a power graph also. Well, when you take the log of both variables, expecting to see straightening, you don't see straightening. So you would have to come to the conclusion that a power function is not my best model for this because the transformation didn't work. Whatever transformation is resulting in this graph, we want to hear about that because that made this thing pretty darn linear. From where it was to where it is now, that's pretty linear. So let's reveal what we did. In this transformation, we're actually going to leave the years since 1970 alone, and we'll take the log of just the response variable. That's what can straighten an exponential model. So again, if you knew this was an exponential model, then it's now you have a tool for doing this. If you didn't know it was an exponential model, you could still do trial and error and figure out, all right, well, when I logged the response and not the explanatory, I got a pretty straight line. That means an exponential model is the best model for this data. The remaining part of this video then is to try to help you interpret the questions and see what kind of answers they're going for. So there's that graph of the straightened data, and they said they used a natural log instead of a log base 10. You notice the graph is pretty much the same, but we do that to introduce E, just in case you come across it. The log base E, or LN, they took the log of the transistors and they left the years since 1970 alone, and this is the question. Based on the graph, explain why it would be reasonable to use an exponential model to describe the relationship between the number of transistors and years since 1970. I can imagine a lot of directions you might try to take that your answer, but I just wanted to show you what they were going for. The idea is, we know from our last two videos that if you leave the explanatory alone and you take the log of the response and you see a straight graph, that means that your original relationship was exponential. That's what that's basically saying. So you don't need to get into the algebra of why. You don't need to get into the reasoning that doubling every 18 months is exponential. You can just use this transformation to say, you log the response, you keep the exponential, the explanatory the same. It must have been an exponential relationship. What's part B? Part B is, well, since you've got a nice linear relationship, do your analysis, and let's see what we could do. Give the equation of the least squares regression line. So good news, this is the easier part of writing equations. You're just writing the equation of the line. Our whole job is, remember that it's not transistors equals, it's natural log of transistors, and you can see that from the graph. When they ask you to make a prediction, good news, they didn't ask us to write the exponential function yet. They're just saying, go ahead and use the linear equation. So there's your linear equation with the 50 years, which is how you would represent 2020, 50 years from 1970. And the right-hand side of the equation turns into 25.4, give or take. But I want to remind you that unwinding natural log of transistors equals 25.4 is about that. E is my base, log is an exponent, e to the 25 is what my transistors is. Predicted transistors is 100 billion. And then finally, they give us a residual plot to go with this thing. So here's the residual plot down there. And they said, discuss what this graph down here tells you about the appropriateness of the model. So that's taking us back to chapter 3, where you say, well, when you see a pattern, we were supposed to say linear is not a really appropriate model. But they go on to say in here that because these values are so small relative to the transformed data, that the model is going to work for us. So that's another one of these places where if you explain yourself well enough in statistics, you can kind of present your findings and just be open and honest with what you've done, and then you can let other people decide if they want to agree with you or not.